on the module outline form, so you don't need to write this down. Yeah. About 9 lectures, depends how fast we go on that. And then I'm going to say a little bit about cathodic protection in practice. Okay, so good morning, gentlemen. You found it. Okay. You were wrong, they did turn up. So there's a sheet going round to sign. Yeah. So then I'm going to say something about cathodic protection, and then Dr. Narracorn's going to do his bit about some of the applications, sweet sour corrosion and control of corrosion in a pipeline system specifically. Okay, so that's what we're going to do. It's always very dangerous talking to a class of master's students because they've all got knowledge. So the first thing I need to do is find out what sort of knowledge you've got, and then I can be very careful and avoid those subjects. So how many mechanical engineers have we got? Okay, 1, 2, 3, 4, 5. Quite a few. Okay. Have we got any corrosion engineers? That's the first thing. Excellent, good. That's a relief. I can now talk about corrosion. Have we got people who call themselves design engineers or design process? Chemical engineers? Okay, quite a few. Civils? Yeah. The civil engineer. Right, okay, so you're the expert when they need to talk about anything civil. Fortunately, I'm not going to, so that's great. Right, okay. I'm sure they've already talked to you about this sort of thing, but just as an aside, you do all have different experiences, okay? You not only can learn from us, but you can learn from each other. Yeah. Okay, so work as a team, learn from each other. Some of you will find bits easy, other bits will be difficult as you go along. I recommend a bit of teamwork. Anyway, that's an aside. So, corrosion. No corrosion engineers. Brilliant. Okay. So, this is a nice, gentle module, okay? It's actually a semester 2 exam, so there's no panic, okay? The exam, when it arrives, is a 2-hour exam, and it has 2 sections. One is the theory side and one is the applied side, okay? So you have to know a bit of my bit and a bit of Dr. Narracorn's bit. What you should be able to do is go onto the web and find 3 years worth of back papers. Not the answers, just the questions. It will give you an idea of the style of the paper. Dr. Narracorn is a new addition to this module, so he might change his bit a bit. Might be a little bit different. My bit's the same as it was. Later on, when you get time, if you look at some of the past papers, you can have a go at a few of the questions. And if you want me to comment on whether I think it's a good answer or not, I can give you some feedback. Okay? We will have, sometime in semester 2, a little, what should we call it? A little, just a question and answer session, where if you found anything as you were going through your revision that you're not sure about, you can ask about it. So there will be a chance for a chat later on as well about the exam. All your modules, if somebody hasn't told you, should have 3 years of back papers available on the web. And if they haven't, you can ask them why not. And generally they should be there, not the answers. There's some people do give out the answers, but legally they're not supposed to. Some people don't read the instructions very clearly. But the questions are there, and that gives you something to have a go at and tells you what the style is. Right. So, reading. There's lots of things that you can have a look at on corrosion. There's a guy called Denny Jones, who's an American, and he's written a book called Principles in Prevention of Corrosion, and it's a nice easy source of reference if you want to pop into the library and borrow it, or you know, you want to read. There's more than you need in here, okay, but it's fairly accessible. There's a slightly older one called Trackaway and Chamberlain. There's another. This is which edition is this? I think this is the. Oh, it doesn't say. As it does. Oh, how exciting! This is the first edition, but there is a second edition, I'm sure. It's an easy read as well, but maybe not as up to date as the Denny Jones book. So I'd recommend the first one, Denny Jones. When you really get into corrosion and you're sitting in your office, your manager's office in the company, and somebody says, we've got this stainless steel vessel and we want to know whether we can put hydrofluoric acid in it or not, you need to go to this book. So don't try reading this. This thing here, Corrosion Engineering, this will tell you whether sulfuric acid, stainless steel is resistant to hydrofluoric acid, or whether structural steel will corrode in mag chloride at a certain concentration. It's more of a reference book than a read, okay? But it's quite good. Mars Fontana, American corrosion engineer, a good reference for data. So that's a read, and this is for data. Okay. Oh, excellent.
For some reason, I'm not in the list.
Ah.
Okay.
Well. Okay, I'll find out.
Yeah, I have, but I have my timetable is as a period.
Fine, excellent. The more the merrier. My mission is to make as many people as aware as possible of how useful corrosion is and how important it is. So that's fine. But we have this list is generated from what they call new contacts, which is a cascade down from SAP, which is, you guys use it as S3P. So this is somewhere in the cascade, but I'll check that. I'll try and find out why. But anyway, that's grand. So we've only got 2 missing. Right. Let's see whether they come next week. Develop a pattern. Okay. It's like a big lab experiment, you know. We create different destinations on the campus, and we see how many of you can get from one to the other, and find it and be there on time. And it's the same. They play the same game with the staff. It's not discriminatory. They give me a timetable, and then they change the timetable as well, which is quite clever. So you turn up somewhere and there's nobody there, and you have to get back log back onto the computer and find that they've moved your location. Because anyway, yeah, that's enough of that. What you want to do is talk about pipelines. So if you want to talk about pipelines, Peabody's Control of Corrosion is a good read, and that's applications. Okay, that tells you about sweet and sour corrosion and cathode arrays and anode arrays, should I say, and that sort of thing. And all these are in the library. I don't know how many copies we've got, but there are at least a few of each. You can also get some of these online, of course. If you get very keen, you can buy a book or two, but I wouldn't go mad. If you ever do decide to buy a book, don't forget you to get 10% off at Blackwell's with your ID card. The other book is a bit of an antique, but it's interesting. There's Parker and Petey, but it's not as good as the first one. So I've sort of put them in order of my preference. Denny Jones and Peabody are probably the two that are worth having a look at, and then the others if you've got time. Yeah. Okay. There we go. So you've got some reference sources now. They've got more information than you need for this module, but that's okay. You might need it one day. You're going to be sitting in an office somewhere and somebody's going to ask you a question. You know where to look it up. Okay. This is my plug for Corrosion as a professional activity. As students, you can become members of either the Institute of Corrosion I-Core or NACE International, which started off in America but now acts as a global body for corrosion. Both good organisations, both provide journals, both online and as hard copies, free membership for students, I seem to remember. And if you're going to go into corrosion at some point, then you know, they like to get you young and work you through it. NACE does a load of certifications, so they have certifications for coating inspectors, for inspections of painting, and so on. So it's a good place to be. And for my sins, I'm actually a member of both of them, so I'm plugging both of them. Okay. Right, that's the intro. We'll now start thinking a little bit about corrosion. As we're going along, incidentally, if you've got any questions, any thoughts, I'm happy to talk to you. It's a small enough group for us to have a bit of a chat. Okay. The only thing I should add is I'm not an applications person, so I can't tell you a great deal about what happens in the field. I know the theory. I've tested pipeline material for 25 years. I know about the microstructure and the grades and the welding and the testing the samples, but what happens actually out in the field where they're digging the trench or laying the pipe on the seabed, I'm not an expert. Okay. So let's start at the very beginning. What is corrosion? Well, it's a spontaneous process. Okay, it just naturally occurs, and it's really turning materials back to their natural condition. And of course this year they put me into a lecture theatre that has wooden surrounds to its screens, which is really annoying, and quite a lot of the lecture theatres, they have large aluminium frames to the screens, and what I say to people is, actually the door handle will do, that's aluminium, alloy, and the only reason why it's not corroding away is because it's developed a surface film that protects it from further attack. And that's the same thing, the similar thing that happens to stainless steels. So, and if you haven't got a natural oxide protective coating, then we give it a coat of paint, and that slows it down.
So,
Yeah.
so the degradation to plastic materials, is it called corrosion?
Ah, good question.
Yeah.
About 20 years ago, we started talking about degradation of materials. It was like nano is a buzzword now. Degradation was a sort of little bit of a buzzword. Degradation is fine. You can apply that to all materials, ceramics, polymers, metals. But corrosion, I would argue, is a means oxidation, and therefore Does a polymer oxidize? No, not really. What happens is you get delamination of the fibres from the resin and things like that. It cracks. There might be a little bit of photo-oxidation, the UV attack. I think I would say, I'm just going to talk about metals and alloys. I think I would say it has to be an oxidation process. And providing it's oxidation, then it could be in another material.
Because in Mass Internationals, said that corrosion is degradation of the materials. So it extends for all
well, I would argue with them. Because corrosion, as far as I'm concerned, corrosion is either what we get most commonly, which is sort of aqueous corrosion, or dry oxidation, which you get in flue chimneys and things like that. And they're both oxidation processes. We'll go on to it later on, but it's a bit like hydrogen embrittlement. People call that corrosion. No, it's not. There is no corrosion in hydrogen embrittlement. It's a cathodic process. No corrosion whatsoever. It just happens that it's because it creates cracks. People say, oh, it's just like cracking and corrosion. They're related, but they're totally different mechanisms. So there is a problem with the literature. Okay, we've got global communication and rapid communication on the web, and people write things, and things that are sometimes wrong spread so quickly that they never get. It's too late to correct them. So there's a lot of misinformation out of there, and sometimes this. I mean, you're probably old enough to appreciate this, but some people aren't. If you really want the definition, probably go back to a book that was written in the 1960s, and that sounds terrible, but they probably wrote it right then because you wrote something and somebody checked it, and then it got to an editor who checked it again, and it didn't go out. It just didn't suddenly appear on the Ethernet before it was edited, and so there's a lot of good quality definitions and information that is sort of pre-web. I know that sounds terrible, but it's true. And there's a lot of stuff on the web that's a bit. So I would say corrosion implies oxidation, and therefore, unless your degradation involves an oxidation step, then it isn't corrosion. Okay, so if it's UV degradation of polymers and the ultraviolet has oxidized the organic compound, that's fine. If it's cracking of the plastic because of the loading on it and its shrinkage with time, and there isn't an oxidation reaction going on, then no, that's not corrosion, it's degradation. Yeah, okay. It's quite a fine point, but it's interesting. Right, so it's a spontaneous process, and the word itself comes from the Latin corrodere, to gnaw away, and that's quite a good description of it, and gnawing away at the surface of your component. Okay, what drives it all? The second law of thermodynamics. This is the worst bit of news that you've ever had in your life, the second law of thermodynamics. If you think about it, I'll let you write it down and then I'll tell you about it. Okay. When we get a corrosion process, we take a pure metal or alloy and we oxidize it. We produce oxides or chlorides or whatever the carbonates, whatever the corrosion product is, from the parent metal. And that increases the disorder in the system. Okay, because you've now got a mixture. You started off with pure metal or alloy, and you've now got a mixture of metal and alloy, and oxide and corrosion product. So you've got a mixed system, and that has a higher entropy value. So corrosion involves an increase in entropy, and that's really why it's spontaneous. This second law is really bad news because it applies to everything, and from biological systems to metals and alloys. And so we are constantly fighting entropy. You get up in the morning, you have breakfast, you consume some energy to create new cells to replace dying old cells. And the process that's causing them to keel over is the increase in entropy. So you're burning energy to fight this second law. And it's the same in corrosion. You can put energy in the system to slow the corrosion. But we'll come back, that's catalytic protection essentially, but we'll come back to that later on. So it's thermodynamically driven. This process will occur. And the only question is, how fast will it occur? Is it going to occur over 30 years, in which case that's the lifetime of the plant, no problem, or is it going to occur over a couple of years, in which case you're in deep trouble and you're going to have to replace the components? So it's the speed of the process that's of interest. There's not a lot you can do about the fundamental driving force for it to occur. It is going to occur. And that's why corrosion engineers are never out of business. Okay. There's always something to do. Oh yes, this is a note saying, put that on, see whether it works. Yes, it does, sort of. Will it behave itself? Well, that's better. This is a sort of chemical view of what happens. This is entropy on one side, composition on the bottom, and it's just sketching that for the spontaneous process, the equilibrium point, the balance between the reactants and products, or the alloy and the oxides created, is at maximum entropy value. So putting graphically onto the board what we put in writing just before. There's another little bit about the maximum entropy position, and that is you can actually come to it from different directions. Some systems, it's interesting to see that you arrive at the same corrosion product through a different route. And the chemists and so on are quite interested in equilibrium because they say it's dynamic. That is to say, when you get to the equilibrium point, there's a little bit of metal turning to corrosion product, and there's a little bit of corrosion product turning back into metal. So it oscillates a little bit back, forward, back, forward, back, forward, back, forward, with the average composition being the maximum entropy. You maybe not need that detail, but it's, if you're a chemical engineer, you think, yeah, okay, I can see where it's coming from. So the important thing is, spontaneous processes like corrosion, you maximise the entropy of the system. Okay. Happy with that? Yeah. Okay. Here's another sketch. This is energy, okay, chemical energy at the side against time, log time for this particular example. Again, the details aren't too important, it's just the concept. Basically, the materials that we extract from the ground as ores whether it's bauxite for aluminium ore, or hematite iron ore, or pitch blende for zinc, are oxides and chlorides and so on. And what we do is we refine them, we put energy into the system to generate our pure metal to make our alloys with. And so the corrosion process, in a sense, is just trying to return the material back down to a lower chemical energy condition. And you don't particularly need the details, it's just the concept that the natural condition for the material is as rocks in the ground, as ores and of oxide and sulfide and chloride and so on. So that's their natural condition, and we're artificially refining them to a more ordered, lower entropy condition so that we can use them, so we can process them to make pipe, make shapes and components. But they're not happy there. That's a high energy, unstable state. So they want to go back again. And the route back isn't always quite the same. So this is one corrosion process which might lead on to another, which might eventually lead back here. The corrosion isn't automatically one step up, one step down. That's all that sketch is trying to show. Yes, sir.
So the iron ore there is in equilibrium.
Yeah. The lowest energy state with the highest entropy is the equilibrium state with the environment. Yeah. And it may have taken thousands of years for it to get to that equilibrium state underground, but it's happy there. And then we come along and throw energy at it because we want the ductility in the material so that we can shape it. So it's more the principle than the drawing that I'm after. If you've got the principle, yeah. Yes?
Is the chemical energy same with terms chemical potential?
Yeah, you can use chemical potential if you want. I suppose, yeah, you can. I mean, if you wanted to be, if you wanted to be particular, you could then say, why don't we call it Gibbs free energy? And you could use that, but yeah, chemical potential, chemical energy is the same sort of thing. Okay, happy with that. Yeah. Okay. Here we go. Why study corrosion? As I said, this is a part of our general intro. Well, the answer is there's an awful lot of money involved in corrosion. It is a huge problem for all the industrialised nations of the world. The estimate is about 3.5% of the gross national product of every industrialised nation is spent on corrosion. That's a huge amount of money. It's great. And it's getting worse. Not only have we got, in Europe, ageing plants, so we're getting more failures, but there is now a load of litigation in health and safety and environmental impact costs being added to the raw cost of repairing the damage. So we've got a situation where it's getting even more serious because of the implications of the failure in environmental impact and people getting sued for injuries and so on. Later on I'll show you some pictures of some of the pipeline explosions in Canada in the 90s, and they look like bombs have dropped, trees are flattened around the area and so on. Fortunately they're out in the middle of nowhere, but potentially and certainly his environmental impact, they're not good. So, it's a very expensive activity. And the people who are at fault, we'll come back to them later on, are the accountants and the design engineers. And they conspire together to devise repeated corrosion mistakes. And so once you've got a handle on how the corrosion occurs, you begin to see patterns, and you think, oh, that's back again. Somebody else has got the same idea. The computational work that's done in design and in finite element analysis and CAD is staggering. I'm just old enough to remember when we did it all on paper. It was all done manually at one point, and now it's all on computer, and it's absolutely staggering. The trouble is, it's like computer games. You get hooked, and you get hooked on the finite element analysis. You get hooked on the CAD package, and everything else that you've learned goes out of the window. So you forget about your material selection and your corrosion and the fatigue resistance, and suddenly you're designing something that looks beautiful but actually is structurally, mechanically unsound or short life, or or the data's rubbish. It's amazing how many people will, if the computer gives you a number, they'll write it down. Just always question the number. Okay. I see regularly. I see PhD theses with finite element analysis, and I look at the data and say, that stress level on that plot is higher than the ultimate tensile strength of the material. That component isn't there any longer; it's gone. As soon as the material gets over the yield strength, it's distorted. So, you should, by all means, use the technology, get the data, but always then try and link it to reality, question it. Never believe the machine. The machine is wrong, quite often. Or it's only as good as the person that programmed it. And the person that programmed it might be wrong. That's the real thing. The machine's okay. And it actually, we've got time to tell you a story. If you go into Marks and Spencer's and you do your shopping, you go to the till, they scan it all and they tell you how much it is, and you pay. I used to go into Marks and Spencer's, and on fairly regularly, just because at that time my teaching slots were, I could go in at that time, and there was an old guy in there, and he must have been a retired accountant, because he knew the value of his basket. And you learned not to get in the queue behind this guy as he got towards the till, because he would say, no, it's not. And they would have to go and check everything, apologise to him and give him tuppence or whatever the difference was. And that was happening on a regular basis. And it's because we accept what the computer tells us. And not always true. And so, some of the supermarkets, I'm not accusing Marks and Spencer's of this, I'm sure, a very good company. I think the recording's on, isn't it? Excellent company. But I suspect some of them are saying, we'll just nudge the till a bit because that will compensate us for our losses from the shelves, from theft and various other things. I might be wrong, but it's all part of our belief that the computer data is spot on. And you as engineers have got to analyse it, critically analyse it. Is it realistic? How does it match up to the mechanical properties of the material? Can that really happen in reality? Okay, anyway. So, plants getting older, environmental and health and safety impacts, costs are going to continue to climb. That's a blank, so that must mean I was supposed to tell you something else. Let's have a look. Oh yeah, okay. This is a picture of a Royal Navy ship from 1763. It's a wooden frigate, a fighting ship, and one of the things that they were very concerned about in those days was the manoeuvrability, the speed at which these ships could go through the water. Trouble with old wooden ships is they tend to get barnacles and biological material fouling the hull of the ship, and that slows it down. Okay, it doesn't go through the water so fast if it's got a load of rubbish sat on the bow of the ship. They came up with a solution: copper. And copper is a biocide; it kills biological material. So if you nail copper sheets onto the hull of your ship, no more fouling. Okay, stay streamlined to go fast through the water. Excellent. So this ship and its sister ship in 1763 were sent out on patrol and went to across the equator, and the copper cladding that was nailed to the ships was reported to be falling off. And they did a complete investigation. And this is the first documented example of what they call galvanic or bimetallic corrosion. What they've done is they've taken a load of iron nails and nailed the copper onto the ship wooden hull using those, and you've got a galvanic couple then where the iron nail is the anode and the copper sheet is the cathode, and we'll talk about galvanic corrosion later on. And so the iron starts dissolving away into the seawater, and as those nails corrode away, then the panels start falling off the wood. Fine. They even recorded an observation. If you've ever ordered a bearing or a fine mechanical component, it'll come in a waxed brown paper. I don't know whether you've seen that. It's a standard traditional wrapping for making sure that the goods don't rust or get damp before they're delivered. And the nails were the same. These packets of nails that were delivered for this job were delivered in wax paper. And in those days, nails, instead of being drawn cylindrical nails, were what they call cut nails. They were square section, manufactured by a chopping process. And you just turn it around and bend it with a square section nail. So it's quite easy to get rough corners and rags on the nail, and you get little bits of wax paper caught up on them. And these guys even recorded that where there was a bit of wax paper between the head of the nail and the copper plate, then you didn't get any corrosion occurring. So if you break the circuit between the iron nail and the copper with an insulator, it stops the corrosion. Fine. Beautiful. Excellent. Organisation. Recorded it, written it down. Excellent. These are some belts from a submarine from 1962. It's a long time ago maybe, but it's the same organisation and it's exactly the same fault. These are supposed to be about 10 millimetre diameter, about 100 millimetres long. They're steel belts, and guess what they were used to clamp onto the outside of the submarine? A copper plate, an evaporator plate off the cooling system for the submarine. Exactly the same problem. Copper and steel exposed to seawater. Same organisation. They'd already done the research and knew what would happen, but some designer got so hooked up on designing his submarine that he forgot to think about the material selection. And that keeps happening again and again and again. The designers forget about the material selection, and that's why the corrosion engineers always make money, because the problems tend to be repeated and mistakes happen again, and you think, oh, I haven't done that again, but they have. So it does keep happening. Let's put that on. So this is just a note about declining costs. We are making new alloys and new materials that are more corrosion and degradation resistant, but we've got a lot of aging plant, particularly in the older nations like the UK, in terms of the industrial revolution. The designers forget what they're doing.
What do you mean by false economies?
Yeah, it's a good question. I'll give you an example in a minute. This is where the accountants come in, and they tend to do everything on a 5-year cycle. As far as they're concerned, the problem's gone after 5 years. They write it off, depreciation or whatever they want to do, but they tend to cheapen the material selection, and as a result you get more failures. I'll show you well, okay, I'll do that one first. Why not? I'll show you that first and then we'll come back. Okay. Oh, that was the submarine. Don't worry about that. Yeah, this is the one. This plot is connected with life cycle costing. So it's the cost for some plant against time, and there are two options here. You can either use a cheap material, have a low capital cost for your structure or network of pipes or whatever it is, and then keep doing repairs, and over time the costs begin to rise. Or you can use a high quality initial material for your construction, and you have smaller amounts of ongoing costs. And so there's much more interest now in what they call life cycle costing, and we're finally beginning to convince some of the accountants that it's maybe better to spend the money now than to spend a load of money later on, and unknown quantities of money, because you don't know exactly when the failures are going to occur and how much they're going to cost you. And that gets even more exciting as you get into the question of, oh well, is there a environmental bill, and is there a legal bill, and so on. So the argument is that if you build quality to start with, then you don't have so many problems later on. This sort of thing is terrible from a corrosion engineer's point of view. You know, we want you to build cheap and horrible, and then we can keep fixing it. Steady income. This reps corrosion income. But no, there's quite a few packages out there, and people are beginning to do these calculations when they're planning plant. Okay. A few artists out there. I'll just go back because the other thing I wanted to say was, one of the things that we are doing is trying to go to more aggressive environments. So we're extracting the oil from lower down in the ocean. We're dealing with oil with higher hydrogen sulfide sour gas type situations than we used to. We're having to run things. We want to run engines hotter. We want to run pipes at higher pressure. We want better mechanical properties generally from our materials, and so everything's getting pushed. And that means, okay, you need to understand the microstructure and the corrosion side of your materials if you want to use those aggressive environments and get more efficient use of your plant. So that's another issue, is we're pushing everything a little bit harder. Okay, I think we've got there for today. Any questions? Anything worrying you at all? No. Good. Excellent. I'll see you next week, and we'll talk a little bit more about the introduction to corrosion. Thank you. Hi.
I've been waiting for this class to have a presentation and information. I'm waiting for this class
Right.
to meet you.
Okay. What sort of project do you have in mind?
Corrosion. I have interest in corrosion. I'm looking at fault analysis, something like that.
So there are several aspects to designing a project. The first thing to do is to think you're probably going to add the project title to your CV. Not the details, just the title. So the project title needs to include something that attracts the employer to what you're going into. So you've got to think about where you're going to put your applications in, and make sure the project title fits with that area of expertise. The next thing is the project should build on your strengths. So if you're good at computational work, best to do a computational project. If you're good to do with laboratory work, best to do a laboratory project. If you're good at and so on. So a project should really relate to your strengths. You probably need to think about, because it's a huge subject. What you've mentioned to me so far is a sort of review project. That's fine. People do reviews, people do practical work, that's fine. If you can come up with a sort of an outline of what you're thinking of, you can email it to me. Think about it. Tell you whether it's in my field or whether it's one of my colleagues' field. Okay. Yeah. I don't think he's particularly a corrosion guy. Dr. Norman, Dr. Rose Norman, he does a little bit of modelling and stuff. I mean, I could do, if it's the right topic, you can take 3 or 4 projects from this group. So that's not a problem. You can do a project with anybody in the engineering section. It could be a paint engineer or a mechanical engineer or whatever. It's just matching up your interest and their interest. If you can, fit it outline, you can get an idea by looking at the staff profiles and see what sort of things we're doing. So I do a lot of stress corrosion cracking and hydrogen embrittlement on pipeline steel. as measurements of samples in the laboratory.
So more of
Yeah, I'm more on the practical side of them. But I've had modelling projects on FEA and also on things like economic costing of offshore plant disposal. What else have I had recently? There's been quite a lot about economics of CO2 transport. Had a dissertation on that last year. Various things. I'm trying to think. But I'm not putting off that. Yes, we might find something that matches. But we've got time to develop that. I think you need to put your titles in before Christmas, before the end of the year.
maybe
I think so.
we've
I
not
think.
had a class
Oh,
on
right. You're going to get asked to provide a supervisor, a title, and a page about what it's going to be about. So, yeah. So it's worth planning. You're doing the right thing. Go. Hello.
Just wanted to apologise for shooting out the call.
Oh, don't worry about it. Yeah. Sorry, please.
And then the other thing I just wanted to say is I'm currently working full time while I'm taking the
Right. So that's a challenge then.
So unfortunately, I'm not always able to attend the sessions. So
Right.
I don't know if there's any way we can.
Interesting.
Is there any way we can make it work, or you have any reference text that I should look at? Or,
Well, those two that
I've
I've given you will be a good start. Everything I think I've done. My problem is that I don't want to have this slides there. I then start to acetate things.